So last class we talked about some of our intermolecular forces, forces that exist between molecules. We had our weakest force, the force that everything has, dispersion forces. Dispersion forces are where your electrons are just randomly in one place or another, and sometimes they decide, or they just are kind of all on one side, and so that side, because there's a bunch of electrons, it's partially negative, and then they're back and evenly distributed. We also had our dipole-dipole forces, our polar forces. So polar molecules have a positively charged end and a negatively charged end. It's only a partial positive or partial negative charge, but it's permanent, and so it's stronger because it's around more than dispersion forces. And then we have our super dipole-dipole force, our hydrogen bonding, and that's the one that we've talked about most recently. And hydrogen bonding, just as a reminder, is bonds, or is existing in things that have bonds directly between hydrogen and nitrogen, hydrogen and oxygen, and hydrogen and fluorine. These are the only three cases where we can have what we call hydrogen bonding. They can get really close to each other, and the nonmetals here, other than hydrogen, the other things, the nitrogen, oxygen, fluorine, are also really strongly electronegative. So we get the maximum charge separation across this bond, and then we get dipole-dipole forces. So it is an intermolecular force. It's between two molecules rather than we're talking about within a molecule. Okay, so keeping that in mind, our quick little review. Which of these do we expect to have the higher boiling point? Which one is going to boil at a higher temperature? HCl or HF? Why? As the temperature increases, the amount of energy, the vibration of the particles, the molecules, the liquid things, increases. They're vibrating more strongly, they get more speed, they get more energy. So as we're increasing the temperature, they get a little bit more rowdy, rambunctious. If we have really strong intermolecular forces, we can think of that as like really strong glue kind of between the molecules. They're going to be really sticky, really tacky. They're not going to be able to separate. If we've got really weak glue, if we've just got like Scotch tape holding two cars together, the cars are just going to drive away because they've got a lot more force than the glue that holds them together. If we connect them with like steel beams and like weld them onto the cars are not going to be able to drive away because they're held together much more tightly. That's like our hydrogen bonding. So our hydrogen bonding is a really strong intermolecular force. It takes a lot of energy for those molecules, those particles to separate. The one that has the higher boiling point is HF. HF has hydrogen bonding. HCl, on the other hand, it doesn't only have, but its strongest force is dipole-dipole. Hydrogen bonding is stronger than dipole-dipole forces. Those molecules are going to be stuck together more strongly, and so it takes more energy. We have to jack the temperature up higher for them to separate out into their gas phase. Stronger intermolecular forces, so it takes more energy to separate the liquid molecules. Any questions about that? So anytime we're thinking about boiling point or melting point for compounds, we want to be thinking about intermolecular forces. Stronger intermolecular forces means higher melting point and also higher boiling point. All right, so our intermolecular forces. The physical state, solid, liquid, or gas, of a sample of matter depends on the strength of the intermolecular forces. Do we have dispersion forces only? Do we have dipole-dipole? Do we have hydrogen bonding forces? Relative to the amount of thermal energy. Anything, pretty much, if you take it down to a low enough temperature, if you take enough energy away from it, is going to have a solid state. It's just simply not going to have enough energy for the particles to move around and past each other as a liquid. Pretty much anything, if you get a bit enough energy, like if you send something flying into the sun, right? The sun temperatures of millions of degrees. If you jack the temperature up high enough, the particles are going to have enough energy to separate out. It's just varying degrees in between. All atoms are in constant random motion. This increases with increasing temperature. So higher temperature means higher energy, which means more movement, more vibration at the particle level. Substances that have weak intermolecular forces relative to the thermal energy, it's like at room temperature, things that have really weak intermolecular forces are more likely to be gases. Things like oxygen, nitrogen, CO2, methane, those all exist just as gases because they're not held together very strongly. They don't have strong intermolecular forces, so it doesn't take very much energy at all for them to completely separate from each other as particles. If the intermolecular forces are strong relative to the thermal energy, the sample will likely be liquid or solid. So water is a liquid at room temperature because it has really strong intermolecular forces. Water has hydrogen bonding, so it's a liquid. Hydrogen bonding, which gives it relatively high melting point and boiling point versus other things of its size, because it's really small in terms of molecular weight, molar mass. Or they'll be solids if they have very strong intermolecular forces. Which brings us to solids. There are several types of solids. I think we've talked about them, touched on them very briefly, but now we're going to explore them with regards to intermolecular forces. Solids can either be crystalline or crystalline, where they've got a well-ordered array of atoms or molecules, things that form crystals. Like quartz. Or they can be amorphous, having no long-range order. Glass is an example of an amorphous solid. If you were to zoom in at the atomic level and take a screenshot, take a picture of what it looks like, and then scroll over, however many atoms worth, it wouldn't be the same picture. You wouldn't be able to get those pictures to overlap nicely. In a crystalline solid, if it's a really well-formed crystal, you take a picture, you scroll over a little bit, you don't have to move your picture very far, and it's overlapping. Same exact structure repeating over and over and over versus no repeating structure for an amorphous solid. Quartz and glass are the same, or some of them at least are the same chemical composition. It's just that one's crystalline and the other is just glass. We can break our crystalline solids into a couple of different categories. We can have molecular crystalline solids. Molecular crystalline solids are made of molecules. Surprise, surprise. What kind of elements make up molecules? Carbon would make up molecules, yeah. When we were doing nomenclature, there were a couple of categories, right? We had molecular naming convention. What kind of things were in those molecular naming conventions? Metals, nonmetals, semimetals, metalloids? Which of those three? Just nonmetals. Nonmetals only. Keep your metals out of my molecular compounds. So our molecular solids are going to be nonmetals only. That's what makes something a molecule, or one definition of what makes something a molecule. Ionic crystalline solids, made of ionic compounds. Ionic compounds are a mix of, generally, metals and nonmetals. I say generally because we can have like ammonium, which is NH4+, which is an ion, but it's not got a metal in it. But generally, metals and nonmetals make up our ionic compounds. And then atomic crystalline solids are made of atoms. So we're going to have only one element, and that could be a nonmetal, it could be a metal, it could be a metalloid, anything. Just as long as it's only one element, that's an atomic, or could be an atomic crystalline solid. All right, so our molecular solids, our smallest unit, smallest repeating unit is molecules. These are going to be held together by intermolecular forces. We can have dispersion forces. We can have dipole-dipole forces. We can have hydrogen bonding. So we've got a range of different intermolecular forces that we can have. We've got really weak things, things that just have dispersion forces. They're nonpolar. And we've got relatively strong things like hydrogen bonding. So comparing two types of things that we call ice, regular ice, water ice, wet ice, is held together by hydrogen bonds because it's H2O. It's going to have a relatively high melting point, still not a super high melting point, versus dry ice, which is CO2, is nonpolar. It only has dispersion forces, and it actually doesn't form a liquid at normal atmospheric conditions, and so it turns into a gas at negative 78 degrees Celsius. So generally, these are going to be kind of on the lower side. So generally, low melting points. We're talking about melting points because we're talking about solids. Ionic solids are composed of formula units. So these are things like salts. Salts is just also a name for ionic compounds. So table salt is an example. Calcium fluoride is another example. I think table salt is probably the one that you might want to hold on to in your brain, sodium chloride. These are held together by electrostatic attractions between cations and anions. These are different from intermolecular forces. Intermolecular forces is partial positive and partial negative charges, and these are full positive and negative charges. This is like the difference between the static electricity holding your socks to your clothes when you pull them out of the dryer, or like a balloon getting held to your body with static electricity versus like strong rare earth magnets holding together. That's the sort of difference in force we're talking about. Significantly different. Or like the little shock that you get when you accidentally, you have a little electricity and you touch a door or something, you touch something metal. versus accidentally touching a live wire where your entire arm goes numb maybe. So drastically different in terms of their force. And these tend to have high melting points because they've got really high bond strength. They've got full positive and negative charges. So table salt, for example, you wouldn't be able to melt in your oven. Crank it up to max temperature, put it under the broiler, it's not melting. So that's why I say table salt is a good one to think about. It's a solid at room temperature versus our molecular compounds are all gases or liquids at room temperature. And then we've got atomic solids. So atomic solids have their composite units, their smallest repeating unit as individual atoms. And we can subcategorize our atomic solids. Our melting points for these vary widely. So some examples of atomic solids: iron. Hopefully you know that that's a solid at room temperature. You'd have to take it up to really high temperatures to be able to melt it. Xenon can also form a solid. Xenon, if you look at our periodic table, right, it's in red. It's a gas. It's a noble gas. That's going to have a really low melting point because it exists as a gas at room temperature. All right, so our types of atomic solids. One type of an atomic solid is a covalent atomic solid. These are held together by covalent bonds. Covalent bonds are strong. Remember that our hydrogen bonding force, intermolecular force, you may remember was somewhere between 2 to 5% the strength of a covalent bond. Diamond is an example. There's a repeating chain of just lots of carbons bonded to each other in diamonds. You probably also know that diamonds, notably solids at room temperature. So these carbon atoms, the way that they link up, graphite's also a covalent atomic solid, but diamonds are basically just a giant molecule of repeating carbon units. And it's got an estimated melting point of 3,800 degrees Celsius, which makes our table salt look pretty wimpy. That's like a super, super high melting point. And that's because of very strong covalent bonds. Here's diamonds. Here's a picture of a diamond. Thank you, government. Our tax dollars at work, getting us this picture of a rough diamond. And this is like what the crystal structure of a diamond sort of looks like. You don't really need to know these things. I just thought pictures would be nice. But we've got this repeating structure of a diamond. Repeats over and over and over throughout the diamond. Another example of a covalent atomic solid that I think is really fun is called buckyball. And it's got one of the Buckminster fullerenes, as they're formally called, their full name, is just C60. That's the whole formula. And it's just carbon in the shape of basically a ball. So it looks like a little soccer ball. There's other Buckminster fullerenes that are also fun that have different numbers of carbons. So I think that's fun. We also have non-bonding atomic solids. These are held together by dispersion forces, and dispersion forces notably very weak. The weakest of the intermolecular forces. So solid xenon would be an example of this. Xenon has a melting point of negative 112 degrees Celsius. Helium, I think, doesn't form a solid. Otherwise, we'd use helium probably as an example. But helium's got a boiling point of 4 Kelvin, which is like minus 269 degrees Celsius. So that's a super, super low super low melting point because of very weak forces. So it's the other end of the spectrum for atomic solids. There's no bonds formed, it's just dispersion forces. And then we also have metallic atomic solids. And metallic atomic solids have the largest, or one of the bigger swings in terms of melting point range. So some examples of metallic atomic solids are mercury. Mercury, famously a liquid at room temperature. You can like play with little beads of mercury in your hand or whatever. Just don't breathe in the fumes because it's bad for you. But iron, of course, melts at a much higher temperature. So we've got varying melting points for metallic atomic solids. Our simplest model of a metal would be something like this, where we've got all of our nucleuses as these positive bits, and their electrons are just kind of like free-flowing between them. They're just kind of loosely shared. It's very hippie vibes. In terms of like the electrons, they're kind of free-range electrons, which probably, why they conduct electricity really well. All right, let's see if we can identify these crystalline solids as molecular, ionic, or atomic. This is for you to try, so take a moment. Give it a shot. So that was a short amount of time for us. So let's try to identify these as molecular, ionic, or atomic. And I think that the easiest way to identify these solids as molecular, ionic, or atomic is thinking about, are they molecules, are they ionic compounds, or are they just atoms? So what is NH3? Is NH3 molecular, ionic, or atomic? It is molecular. It's molecular because it's a molecule. So it's just nonmetals, nitrogen and hydrogen. How about runs batted in? Is that a molecular, ionic, or atomic? It is ionic. So RBI is ionic. It's got a metal and a nonmetal. And then last up, we've got krypton. Is krypton molecular, ionic, or atomic? Yeah, it's atomic. It's just one thing. If you had to guess, would you say that krypton is a covalent atomic solid, or if it's a solid, is it covalent, is it non-bonding, or is it metallic? Covalent, non-bonding, or metallic? Is krypton a metal? It is not a metal, so we can cross out metallic. It's definitely not metallic since it's not a metal. What kind of thing is krypton? It's a noble gas. So it is non-bonding. Noble gases hate bonding. You can make them bond, you can force them to bond, it takes a lot of energy, and then as soon as they possibly can, basically they say, no thank you, and they undo the bond that you've done. Just as a general rule of thumb. All right, we've talked about gases. That was kind of like all of last chapter, right? So we're going to do a little bit of review about liquids and solids. In gases, of course, our molecules or atoms are separated by large distances. That was one of the points in our kinetic molecular theory, one of our 5 points that you're supposed to know. In solids and liquids, our molecules or atoms are touchingly close. There's no empty space between them. Or at least there's very little. It's an insubstantial amount of space between them. The difference between solid and liquid is the degrees of freedom, how much they're able to move relative to each other. So the example that I like for solids, everything's kind of in its own spot. It can move around in its own zone. This is like people at a movie theater. Generally, you go to a movie theater, everyone's watching the movie, they're drinking their popcorn, they're eating their soda, right? They're snacking on their candy, they're having a good time, hopefully. They're maybe whispering to their neighbor. They are not playing musical chairs inside of the movie theater. They're not all getting up and walking around and milling about the whole time, unless it's like some sort of new age art exhibit maybe. So that's solids is at the movie theater. They're sitting down, they're in their spots, but they're still moving. They're not. You don't get suspended in time usually when you go to the movie theater. In liquids, our atoms and molecules are free to move around each other. So this is more like people kind of up at the front at a concert or maybe at like a big festival, like if you Lollapalooza in Chicago, right? There's tons of people out there. They're all kind of in a confined space. They're generally pretty packed close to each other. They are not confined to their own spot. You can move around past each other. You can try to make your way up to the front. You can leave and go to the bathroom and come back. That's more of our liquids sort of thing. Tightly packed, touching close, maybe uncomfortably close, but free to move around each other, not locked into your own spot. And these are images of what, or representations of what those might look like. So if we have solid oxygen, everything's nice and neat. Those are still vibrating around. The vibrating part is not shown here, but they're kind of like locked into their spot. In a liquid, these things can be moving around and past each other, and then we've got empty space in our gas. Locked in place for our solid. Free to move past each other in our liquid. And just straight up free to go wherever they please and not be tethered to their neighbors in a gas. I think these are slides that we've seen before. I'm pretty sure I've shown these before. So we've got very low density for our gases because of the empty space between them. They've got indefinite shape. They'll fill up the room. Smells travel, right, because of that indefinite shape. You can also compress them, and they generally have weak intermolecular forces relative to thermal energy. Our liquids have high densities compared to our gases. We have indefinite shape. They can move/change shape. If you, spill your milk on the ground, it doesn't just flop onto the ground in the shape of the container that you were drinking it in. It will spill all over the floor. So it'll assume the shape of their container, but it has definite volume. It can't be easily compressed. Squeeze on a container of any liquid as hard as you want. The container will give way before the liquid starts to compress to any serious degree. And these have moderate molecular forces relative to thermal energy. Stronger intermolecular forces than our gases. Our solids also have high densities in comparison to gases. So in that way, they're like liquids. However, they have a definite shape. So this is unique to our solids. They also have a definite volume. You can't really compress solids. And these are the ones that can be split into crystalline, ordered, or amorphous, disordered. And these tend to have strong intermolecular forces relative to the thermal energy. So like our covalent solids are things with hydrogen bonding, perhaps. That's not that interesting. Solids have definite shape. I think we know that. Okay, some other fun things that come along with intermolecular forces: surface tension and viscosity. If we didn't have intermolecular forces, I mentioned this last class, we wouldn't have solids and liquids. It would all be gases, and that would be very boring because we wouldn't be here. We just wouldn't exist. We would just be gases floating around, and that's not very fun, probably. In liquids, we get surface tension and viscosity. These are the result of intermolecular forces. So surface tension, this is a thing that you can try at home. It is relatively free, low cost. If you take a paper clip and you very carefully set it down on the surface of water, it will sit down in the surface of the water, right? So you can see sort of the water deforming around where the paper clip is sitting. It's held up on the surface of the water. You can also do a similar thing with a needle. There's like a trick. If you, for some reason, need a compass and you've got a magnet and a needle, you can magnetize the needle and then set it on the surface of some water, and it'll make a little rudimentary compass for you. You don't need to know how to do that, of course, but the reason that that's held up is because of surface tension. Our formal definition for surface tension is the tendency of liquids to minimize their surface area. And I think we've got a slide coming up that's about that. Try this on something that's got less strong intermolecular forces, like gasoline, which I don't recommend because you shouldn't be touching gasoline or smelling gasoline for too long, as fun as it is to smell. That's not going to work. It's going to drop straight in because the intermolecular forces aren't as strong. It's got less surface tension because of the weaker intermolecular forces. So here's a picture of our favorite insect using surface tension to sit up on the surface of the water. And a look at what's going on with the water molecules themselves, just represented by blue spheres. So the reason that surface tension exists is that surface molecules are pulled in every direction that there are water molecules. So at the surface, there's no water molecules above you. There's only water molecules around you and beneath you. And so the water molecules on the surface experience a net pull down and kind of across. But the net force that they're experiencing is down. And so it kind of pulls the surface of the water close. It's pulling the water molecules down versus the molecules on the inside are pulled every which way. Surface tension is the reason that water droplets form. Like if you drop some water on the countertop or whatever and it's not a porous surface, it'll form little beads of water, and the bigger the beads the beads will form bigger beads if you've got stronger intermolecular forces. So if you spill like hand sanitizer on the countertop, it's going to just run all over the place, versus if you spill water or something else that has strong intermolecular forces, it's more likely to clump up in little water droplets. That's also something you can try at home. Just don't make too much of a mess. Surface tension is also the reason why jumping into water from really high elevations is bad for you, because you hit that surface tension and then goodbye ankles, nice knowing you. If you break up the surface tension, so like there's a trick for people that jump from really high, like do really high jumps. They spray water on the surface and that disrupts the surface tension, and then you just go straight through without breaking your legs. hopefully. Also, if you're up on the space station, on a space shuttle, where there's little to no gravity, you can get really big drops of water that are just floating around. And this is probably kind of a bold picture for them to take, because generally just having water floating around is probably not a great thing to have. But it's a cool picture. So surface tension is the reason that we get these nice pictures of water as spheres. Another property that's brought on or due to intermolecular forces is viscosity. Viscosity is the resistance of a liquid to flow. You could also think of it as like the thickness of a liquid. So more viscosity, thicker liquid, or higher viscosity, is a thicker liquid or fluid. Viscosity, for some reason in my mind, it took a long time for it to click. I always got it flipped the other way. I thought viscosity was like things that flow really easily. I don't know. So some examples of things that are more viscous versus less viscous. Motor oil is more viscous than gasoline. Motor oil is kind of thick. Honey is more viscous, or like maple syrup, both more viscous than water. They flow more slowly than the other thing. They're also more likely to clump up and stick together. And viscosity is greater in substances that have strong intermolecular forces. The molecules have trouble moving around. They're closer to becoming a solid. So they get a little bit slow and slushy relative to just like the regular liquid state. Here's a picture of someone pouring some honey. Honey, famously very viscous. Wait. Thanks to sugar and other things that are going on in there. Do you have any questions so far about intermolecular forces and things? If the viscosity gets high enough, will it become a solid? I don't think so. Maybe. It might become solid-like. I think it would still technically be a liquid until it's a solid. I'm not sure. That feels like a philosophical question. But you can get things that like flow really, really slowly to the point where they look like they're a solid. But then if you like wait for hundreds of years, oh no, it's actually moving. There's like a Millikan's oil drop experiment, I think, is sort of something along those lines, where they just took some tar and put it in a funnel and then left it for a long time, and then it flows really slowly. So that's sort of like approaching that limit of, is it a solid versus a liquid? All right, so some of our phase changes. As you increase the temperature of a solid, like ice, you're increasing the vibration, you're increasing the energy of the people at the movie theater. Eventually, if they get enough energy, they will get up out of their seats. They'll stand up and start moving around. And the same thing is true for solids. Solids, they're locked in place, but if you give them enough energy, then they'll eventually vibrate fast enough, they'll have enough energy that they can break the bonds with some of their neighbors, and they can move past each other. They can't break the bonds with all of their neighbors, but they can move past each other. So they have enough energy, to move past each other in melting, and that turns them into a liquid. Now they can slip and slide past and around their neighbors. That's what happens at our melting point. So when we've got melting, our water molecules are breaking free from their solid structure to become a liquid. If you have ice and water present, the temperature will be 0 degrees Celsius under certain conditions. Generally speaking, that's going to be true. Regardless of how much ice and how much water, if it's well mixed, you're locked in at 0 degrees Celsius. So one of the takeaways here, people that drink ice water, you like a lot of ice rattling around in your cup, you like the cold, refreshing taste of ice water, you're getting a consistent drinking experience. You're getting 0 degrees Celsius water into your mouth. If you're a little bit bold, if you're a little bit adventurous, and you drink just room temperature water, no ice, who knows what temperature you're getting. It could be really cold. It could be 2 degrees Celsius. Could be 25 degrees Celsius. You don't know. You're bold, you're adventurous, you like to live on the edge. But the ice keeps it locked and loaded 0 degrees Celsius. Always 0 degrees Celsius. Melting is a type of phase change, changing between solid and liquid gas, liquid and gas, etc. At every phase change, as long as you've got 2 phases of matter, you're locked in at whatever that temperature is. So it's always going to be 0 degrees Celsius. We're assuming that there's good mixing. Sometimes you could have some zones that are a little bit warmer if you don't have ice there. It also takes a lot of energy, which we'll be talking about later, to do the actual melting process. To get the ice to melt takes a lot of energy, and that's got applications for things like heating up butter, especially for cooking. Another phase change that we have is sublimation or subliming. Sublime or subliming. Sublimation is changing from a solid to a gas directly. So no liquid intermediate. When a substance sublimes, molecules on the surface of the solid, remember that on the surface of a solid, they're only held by the things that are underneath the surface, right? So they're not held on all directions, just on one side. They could randomly get bumped in just the right way by like a couple of their neighbors maybe, and boom, they've suddenly got enough energy to break free of all of their neighbors and go straight into the gas phase. Dry ice is a little bit of a weird compound in that it doesn't exist as a liquid at any temperature at normal atmospheric pressure. You have to jack the pressure up quite a bit to get liquid carbon dioxide. So dry ice is a great example of sublimation because of that. Sublimation also has real-world consequences for us, which I think we'll talk about in a couple slides. So there's dry ice in a bowl. There's lots of fun stuff that you can do with dry ice, like carbonating beverages, since it turns directly into gaseous CO2. Just be very careful when you do that because the density of the gas is way lower. It's going to expand and take up a lot more volume. So if you like put a little bit of dry ice into a water bottle or something and it starts to bubble and turn into the gas, there's a very good chance that it's going to explode if you don't relieve the pressure. So don't do it with glass. You can do it with like a plastic container, something where the top will just pop off. So be careful if you do any of that. Regular ice will also slowly sublime, even at temperatures below 0 degrees Celsius. So like if you go to regions of the world where it's always below 0 degrees Celsius, if there's not snow, eventually all of the ice will sublime and turn into gas. It'll just be disappearing unless it's replaced, even if it's always below 0 degrees Celsius. Also, if you leave ice cubes in your freezer for long periods of time, if you're using like ice cube trays and you haven't used them in a while and you go and look in your ice cube tray and you're like, I've got the weirdest little ice cubes in here where they've kind of pulled away from the side of their container, and you're like, what happened here? That was because your ice cubes were subliming. So ice cubes get smaller over time if you don't use them. So it's a good idea to occasionally replace your ice cubes if you're not using them up, or at least check on them. Check on your ice cubes. They might be sad. Ice also sublimes out of frozen food. So if you freeze foods, or if you buy frozen food, it's got ice inside of it, generally. Ice subliming out of frozen food is what causes freezer burn. You've probably heard about it. So if you freeze some food, you're like, this is awesome, I love this food, this is going to be great to eat in 6 months from now, and then you go and open it up, and there's ice crystals all on the inside of the bag. You're like, I didn't put those ice crystals there, where'd they come from? That's the water that was inside of your food. It's left the food and it reformed as ice crystals on the surface of the bag. This will also happen for ice cream. Devastating consequence of not eating your ice cream is that it gets freezer burn. The water leaves the ice cream, it forms ice crystals on the lid, and you're like, where'd those ice crystals come from? I didn't put those there. Those ice crystals came out of your ice cream, and now your ice cream tastes bad. The texture's off, it's wonky. You like want to eat it because it's still kind of tasty, but the texture's throwing you off, and you're like, maybe I should just throw it out and get some new ice cream. So the thing we're learning here today, it's important to eat your ice cream. Eat your ice cream before it goes bad. A way that you can avoid this is by deep freezing. So normally your freezer is not super, super cold. If you can get freezers that go below what your normal like freezer on your fridge goes. So you can get freezers that are good for this. And a lot of commercial facilities that do frozen stuff are going to have a deep freezer. So colder than your normal freezer. And so that slows down the rate of sublimation, and then your food sticks around longer. Sublimation also occurs in things that you wouldn't expect. So if you've ever been around some metal and you're like, it smells like metal. Why does it smell like metal? It's because there's little bits of metal that have sublimed. They've left the surface of the metal that they're sitting on, and you're smelling them. So even metals, even things that are definitely solids at room temperature, can sublime a little bit. And I think I talked about that maybe a little bit in like the first week when we were talking about the International Standard Kilogram, which we don't use anymore. Okay, some other phase changes. Boiling, evaporation, condensation. So evaporation or vaporization, this is our liquid to gas phase change. Rate of vaporization increases with a couple of factors. One of those factors is increasing surface area. So if you've been to a basketball game and somebody falls down on the basketball court, they're really sweaty, so there's now like a big sweat mark on the court. If it's at a professional game, they've just got a guy with like a fancy mop that comes out and wicks it up. But if you're at a high school game, all the basketball players gather around and they make their shoes squeak and they kick the floor where the person fell down. The reason that they're doing that is because they're spreading out the surface area. So they're adding some friction from their shoe to heat up the water. They're also getting the water on their shoe, spreading it around the floor so that it'll evaporate faster since it's already kind of warm. And that's a faster way of getting it to evaporate, and it's a little easier than grabbing a towel, depending on the circumstances. So if you've seen basketball players kicking the ground, that's the reason why they're doing it. You can also increase the rate of vaporization with increasing temperature. So heating something up, it's going to evaporate more. If you, this is related to like steam that you see coming off of food, right? When soup or something is really hot, you can see the steam coming off of it. That's because it's got an increased rate of vaporization to the point that some of it's condensing into steam. You can also get increased vaporization with decreasing strength of intermolecular forces. So the cooling feeling that you feel on your hands if you get acetone or rubbing alcohol on your hands. Acetone, I guess it should be and rubbing alcohol. Evaporate quicker than water. If you dipped one hand in water and you dip the other hand in acetone and then you pull them out at the same time, one of those is going to be dry first, and I think we probably all know that it's going to be the acetone hand that dries first. Okay, another thing that I like to talk about on this slide, there's a trick to drying your hands off with those air blow dryers that I didn't discover for an embarrassingly long amount of time. So I always hated those hand blow dryers because you stick your hands under there and you've got them there and you're waiting and you're waiting and it's blowing and it's hot air, but it's not doing anything. You've still got water in your hands, and then you're like, at some point you just give up and wipe them on your pants and then open the door and you leave. Here's the trick. Rate of vaporization increases with increasing surface area and increasing temperature. You don't have to worry about the increasing temperature part as long as it's blowing hot air. The blow dryer is taking care of that for you. Increasing the surface area though, when your hands are under the blow dryer, right, the water is doing its surface tension thing. It's forming droplets in various parts of your hands that you don't want to be there. You can, of course, shake them off a little bit. You can also rub your hands. Spread the water out over the area of your hands, and then it increases the rate of vaporization, and boom, you're walking out with dry hands and not having to wipe them on your pants or whatever. Or you just, use paper towels. So that's the trick. The trick to dry hands when you're leaving the bathroom, especially if they don't have paper towels. Okay, so all that fun stuff aside, liquids that evaporate easily, faster than water, are termed volatile. So things that basically just have a boiling point lower than water. That's at least how I think of it. It's probably not the formal definition. So things like acetone, things like rubbing alcohol, things like methanol, wood grain alcohol, ethanol, the one that you can drink. Those are volatile liquids. They boil at a lower temperature than water, vaporize more easily than water. Things that don't vaporize easily are termed non-volatile. So in my mind at least, that's things that have higher boiling points or vaporize less easily than water. So here's evaporation. This is sort of how sublimation works, just we're starting with a liquid instead. So remember, because of our surface tension, or when we were talking about surface tension, right, there's stuff on the surface of the water, molecules that are on the surface of the water. They're only held by their neighbors down and to the side of them rather than all 360 degrees. And so these surface molecules only need to get a little bit of a bump relative to their neighbors, and they'll pick up enough energy that they can break away into the gas phase. And that's what we call evaporation. Another thing here, right, in terms of our overall energy distribution, the ones that leave have enough energy to leave. The other ones don't have enough energy to leave. They're stealing energy as they evaporate, which is why that cooling effect, the temperature decrease that you feel, like especially for acetone and rubbing alcohol, like hand sanitizer, that cooling feeling that you're experiencing is because those molecules, when they're evaporating, are stealing energy. they need more energy than their neighbors to evaporate, and that's why you get that cooling effect. Here's one of my favorite graphs that we look at in this class. At a given temperature, any temperature, a sample of molecules or atoms is going to have a distribution of kinetic energies. Some have low energy, some have high energy, and most have what we would think of as medium energy. But it's a distribution, just because of the way that they're randomly bouncing around. And at any given temperature, there's going to be a small amount that have enough energy to escape. We're looking at, on this graph, energy on the x-axis, so things that are over kind of towards the left, those are the very low energy molecules or atoms. On the right side, we're looking at things that have a lot of energy. And then our y-axis is just our number of molecules that are at that particular energy level. So we've got temperature 1 and temperature 2. Temperature 1 is the blue. It's the colder temperature. Temperature 2 is the warmer temperature. For temperature 1, most of the molecules are cold relative to the rest. Right? We've got a big peak over here. We've got a lot of molecules that are kind of lower on that energy side. And we've got this decreasing tail kind of over out here at the high energy level. And we've also got this E that we've got here. So this E is the energy that it takes to evaporate for the molecules to leave. At our low temperature, our blue curve, we've got a small tail that has high energy. Decreasingly small amount of molecules, the higher the energy gets. So even though we've got a cold liquid, we've got some molecules that can evaporate. So evaporation is occurring. If we increase the temperature, that's moving to this red line, we can see that our average temperature, most of our molecules, right, the biggest part under our curve, has moved over to be higher energy. So we've got, on average, higher energy, and our high energy particles, the ones that have enough energy to evaporate, has increased. And this will be true at all temperatures. We're always going to have a big bump where most of our molecules are. That's kind of related to our temperature. And we're always going to have a small tail that goes out into this really high energy zone. There's always going to be some molecules that can evaporate. So always some molecules that can evaporate. And it increases as you increase the temperature. Okay, goodbye, favorite graph. We'll see you next year. The opposite process of evaporation is condensation. So going from a gas to a liquid. So the water that forms, drinking out of if you're an ice water enjoyer, and you're drinking out of a big glass, big plastic glass, you know the one I'm talking about, so refreshing. The condensation that forms on the outside, since those are not insulated, right? That's warm water molecules in the air running into a very cold, refreshing beverage. They lose energy. That energy gets dumped into the glass or the plastic of the cup, and suddenly those water molecules don't have energy to fly around anymore. They get trapped in the liquid state. They've condensed, so that's why you get water buildup on the outside of your glass. There's a point where the rates of condensation and the rates of evaporation. So let's draw a big refreshing glass of water. I guess it's not that big. We're going to have a rate of evaporation, but there's also going to be water molecules in the air that are hitting the surface of the water and condensing. When those rates are the same, when the rates are the same, dynamic equilibrium has been achieved. So it's dynamic equilibrium because liquid molecules are going into the gas phase. At the same time, gas molecules are going into the liquid phase. So there's travel in both directions. That's why it's dynamic. It's not static. They're not just locked in, staying in those same numbers. There's movement in both directions. And equilibrium, the equal part being the rates. So dynamic equilibrium. And when this occurs, we're not going to have a change in the concentrations, but the concentrations will not be the same. We'll talk more about dynamic equilibrium, I think, later. When we are at dynamic equilibrium, there's a term called vapor pressure. And the vapor pressure is the partial pressure. So how much of that liquid is in the gas phase, the pressure from that, that's our vapor pressure. The important part of this is that vapor pressure is at dynamic equilibrium. You can still have a partial pressure of the gas part, but if it's not at dynamic equilibrium, then it's not the vapor pressure, it's just a partial pressure. Vapor pressure increases with some things as well. So we talked about the things that affect evaporation. The things that affect evaporation was surface area, right? The reason you rub your hands together, the reason that basketball players kick the court. Increasing temperature and decreasing strength of intermolecular forces. For vapor pressure increases with two of those, increasing temperature and decreasing strength of intermolecular forces. Vapor pressure does not change. It's independent of surface area, because if we increase the surface area, we're increasing the surface of things that can evaporate. We're also increasing the surface of things that can condense, and since those rates are equal, it doesn't affect the vapor pressure. So surface area doesn't affect vapor pressure. So in lieu of understanding, or instead of understanding the micro part of it, you could also just remember surface area doesn't affect vapor pressure. Let's take a peek at evaporation and condensation. We've got these renderings, water in a sealed container. So in phase 1 here, diagram 1 here, we've got just liquid water. We don't have any water in the gas phase at this point. So the water is starting to evaporate. Some of it is evaporating. And in frame 2 here, the middle frame here, some of these water molecules are coming back down, hitting the surface of the water and getting trapped. At the same time, we still have things that are evaporating. And then we get to 3, we've got things that are condensing. We've got the maximum amount of particles that we can get into the gas phase. They're condensing on the walls, they're condensing into the water. If you leave a closed container out of water that's not insulated, it's clear, like a glass container, you'll get condensation on the walls because of this stuff going on, the vapor pressure being established, that dynamic equilibrium. It's not just going to condense onto the surface of the liquid. We also have boiling. So the boiling point is the temperature at which the vapor pressure, the equilibrium partial pressure, dynamic equilibrium partial pressure of the liquid, is equal to the pressure above it. So what happens at our boiling point is that we've got enough thermal energy that molecules in the interior of the liquid, think like the bubbles that form on the bottom of a pot when you're boiling water to make pasta or something, those have enough energy that they can form gases even inside of the rest of the water molecules. And then those float up to the top because they're less dense. But this pressure above it part is important here. If we've got higher pressure, we'll need higher temperature. The opposite is also true. If you go up to high elevation, your pressure is going to be lower. Since the outside pressure is lower and vapor pressure is affected by increasing temperature, so we increase the temperature of our water, the vapor pressure is slowly rising until it hits the atmospheric pressure, the pressure around it. If the pressure is low, you don't have to bring the temperature up as much. And so the boiling point for water, for any other liquid, is going to be lower at higher elevation. So it might boil at 95 degrees Celsius instead of 100 degrees Celsius, for example. And the higher you go, the lower the boiling temperature gets. So sometimes, like if you're going up to the mountains for a weekend, if you're going to make pasta, you have to add extra time onto your pasta timer because the temperature that your water is boiling at is lower, and so your pasta is cooking less quickly. It'll affect all those sorts of things. It also might affect, if you like tea or coffee, your water is going to be boiling at a lower temperature. It's not going to be as hot. You might need to add a little bit of time to your tea timer or do a little bit of a slower extraction on your coffee to be able to get the same effect. Just like with our melting, which was a phase change, boiling is also a phase change. And so when you're at the boiling point, our temperature is locked or capped. Not in the sense of something being untrue, but in the sense of it's not going any higher. So if you have a mixture of boiling water and steam, like when you're boiling a pot of water, it's got a maximum temperature of 100 degrees Celsius. You cannot take it higher than 100 degrees Celsius. It simply will not happen. All that's going to happen is it will boil rapidly, more rapidly. So any extra energy will go toward boiling. So you don't need a super, super fast rolling boil necessarily to cook something in boiling water. And if you've got to cook it for a long time, it might be a better thing to not have quite boiling. So you might take it down to a simmer. This is also the reason that you can just set a timer when you're making pasta. Because your water is boiling, it's maxed at 100 degrees Celsius, so you don't have to specify what the temperature of the water is. You don't have to put a thermometer in and check. You can set a timer. You know that since your water is boiling, it's at around 100 degrees Celsius, and you get consistent cook times. This was one of the things that I loved about when I took this class. I thought that was so cool. Questions? Okay, so remember, eat your ice cream.